The last point on the curve we're going to consider is something just past the equivalence point. Now at this point, all the silver reacted with all the chloride, and we have extra silver. And the concentration of silver is just going to be this extra silver that didn't react with the chloride and is just excess at this point. In an actual titration, if you're doing this, this would be after your indicators already changed color, and you wouldn't want to keep titrating at this point in reality, unless you were measuring the concentration of silver using an electrode or something like that. But this is more just to understand what's happening in terms of our concentrations as we proceed with the titration. So our first 50 milliliters of silver already reacted. So our excess silver is going to be the extra 2 milliliters. And so we want to know how many moles is that. So 2 milliliters extra times our 0.05 millimoles per milliliter. Right, 2 times 0.05 is 0.1. So we have 0.1. Again, I'm leaving off some significant figures here. 0.1 millimoles of silver. All right, and that 0.1 millimoles is just extra. It's not really doing anything. So the chloride already reacted and formed a precipitate, and so KSP doesn't even matter here because most of our silver is just going to be dumped in from us putting the extra titrant in, as we go past the equivalence point. So if we want the concentration of silver, we know the moles. We have 0.1 millimoles that we just calculated. And we divide by our total volume. So we started with 25 milliliters. We have added 52 milliliters. And so that's our total volume. 0.1 divided by 25 plus 52. Now if we plug this into the calculator, what we'll get is 1.3 times 10 to the minus, I can't read my writing here, I think that's a 3 molar. Let me just double check my math here. If I get this. All right. So double checking the math, we have 0.1 divided by 25 plus 52. And that is indeed 1.3 times 10 to the minus 3. All right. Couldn't tell if it was a 3 or a 5 in the exponent. Okay, but yet again, we see this is still even past the equivalence point, a much bigger concentration of silver than what we had. If we want to write this as the PAG value, this is equal to 2.89. So let's put this all together. What does our overall curve look like, and what sort of is determining what's going on? So we've already drawn the overall shape. But for this specific problem, we have PAG on the y-axis here, volume in milliliters on the x-axis, and we'll put out here, this is our 50 milliliters, because we know this is our equivalence point. And let's see, our value was about 4.87. Let me get the exact numbers here. Yeah, 4.87. So that is one point we have here. We started with something around 10. Our value was 8.5. And then once we get to 52, just past, our value has already dropped to the value we just calculated, which was 2.89. And so the general sort of trend we're going to see is something that looks like this with a very sharp curve here. And continuing on like that. And this is only approximate. I could get you an actual titration curve. We'll look at that in class. But what we can see is here what's going on is we have excess chloride on this point equal here, and here we have excess silver. Excess chloride and KSP controls the concentration of silver. and when they're equal, KSP is what matters. One thing you'll notice is that in our equivalence point determination, the PAG did not depend on any of the volumes or concentrations that were involved. And this is in general true for any titration. The value of our PAG or whatever concentration we're monitoring will only be controlled by the equilibrium constant associated with the reaction. And so what you're going to see is that it doesn't matter. It doesn't depend on the concentrations or volumes that you're working with. You'll always have the same value at the equivalence point. Now that's not true for before and after the equivalence point, and there will be differences depending on concentration for the same titration curve. But at the equivalence point, things will be identical for a given reaction.